Hey everyone, welcome back. In today's video, we're diving into a concept that's not just central to calculus, but also incredibly useful in real life: maxima and minima of a function. You've probably heard these terms tossed around in math class, but what do they really mean? Simply put, maxima and minima help us find the highest and lowest points of a function, like the peak of a mountain or the bottom of a valley. But this isn't just academic theory. We calculate these points to solve real-world problems. Want to maximize profit or minimize cost in a business? You'll need maxima and minima. Designing a road or a roller coaster? Engineers use these concepts to find safe and efficient curves. Even in machine learning, algorithms rely on minimizing error to improve predictions. So stick around, because by the end of this video, you'll not only understand what maxima and minima are, you'll see how they shape decisions, designs, and data all around us. First, let's start with a linear function, f of x equals mx, where m is the slope of the line. As we rotate the line about origin, the value of slope m changes from +1 to -1. So, we can say that if a linear function slope is negative, it decreases. If it's 0, it is constant, and if it's positive, it increases. But what if f of x isn't linear? Consider a function f of x equals to -x squared plus 4x plus 1. As we move over the graph from left to right, the value of function first increases and then decreases. Now, if calculate the derivative of function, that is change in value of f of x, with respect to x, it comes out to be f dash of x equals -2x plus 4. Don't worry, we will learn to compute derivatives rapidly. For now, we rely solely on the definition of f dash of x as the limit, which is equal to limit b tends to x, f of b minus f of x divided by b minus x. Let's see how it works. First, evaluate f of b minus f of x, which after a little bit of simplification is equals to this expression. After dividing this expression by b minus x, give us this expression. And at last we apply limit on both sides. We get derivative of f of x equals to -2x plus 4. Now, if we plot the graph of derivative f for different values of x, we get a straight line that intersects x-axis at x equals to 2, or in other words, the value of f dash of x is equal to 0 at that point. But wait, the function has its maximum value at x equals to 2 itself. So, we can say that, by putting f dash of x equals to 0, we get some value of x, at which function is maximizing. There is one more way of visualizing the increasing and decreasing behavior of the function. If we plot a tangent to our function, then the angle made by this tangent with horizontal is called its slope, and as we glide this line smoothly along the curve, we get different values of slope. For x less than 2, we get positive slope, that is, value of function increases as x increases. For x equals to 2, we get 0 slope, and for x greater than 2, we get negative slope, that is, function's value decreases as we increase x. Let's understand it with real-world example. If we throw a ball vertically upwards and plot its variation of height with respect to time, then we get a similar curve. Here, height is a function of time, represented as h of t, and change of height with respect to time gives ball's velocity in vertical direction, which is equivalent to slope of tangent line on the curve h of t, and at maximum height, this slope, or velocity of the ball, is 0. Let's solve one more example. Consider a function f of x equal to x to the power 4 minus 3x squared plus 2, which has derivative f dash of x equals to 4x cubed minus 6x. After putting this expression equal to 0, we get following values of x. Since we get three different values of x. There happens to be 3 points on the function where f dash of x, or the slope of tangent line on the curve, is equal to 0. Correspond to these 3 values of x. 2 are minima, and 1 is local maxima, that is maximum compared to its surrounding. These values of x, where derivative of function is equal to 0, are called critical points. Sometimes, critical points are not the largest or smallest values of a function. Like in our last example, we get a local maxima at x equals to 0, that is largest function value compared to other nearby points. Whereas, an absolute maximum or minimum has the largest or smallest function value overall. And we can find critical points of a function by finding when the rate of change is 0. Now, since we are able to find the critical points of a function, but how can we tell if the critical point is maximum or minimum? Let's start by observing how f dash, or derivative of f, behaves at these points. As you can see, in the arbitrary curve, near local maximum, the derivative of function f dash of x is of decreasing nature, that is, the slope of tangent changes from positive to negative. And if there is local minimum at the point, then the rate of change of the derivative is positive in nature, that is, slope of tangent changes from negative to positive. This rate of change of derivative is called second derivative, and we read it as f double prime. As we can see from the plots, if the value of this second derivative is less than 0 at the critical point, then the f dash of x is of decreasing nature, or we can say that the function is at local maximum. Similarly, if the value of second derivative is greater than 0 at the critical point, then the function's derivative is of increasing nature, and we can say that the function is at local minimum. In a nutshell, we can figure out if critical points are local maxima or local minima using the second derivative test. First, find the critical point by solving f prime of x equals to 0. Plug those values into f double prime. If the result is positive, the critical point is a local minimum. If the result is negative, the critical point is a local maximum. But there are some limitations of the second derivative test, such that it can't tell us if these critical points are global extrema for function. But that we will discuss in the next video. Until then, goodbye.